So in this video we're going to do another example of calculating flux, and I'm going to use the same velocity field just as before, but now we'll work in 3 dimensions. So my velocity field in this case is going to be x times I hat plus y times j hat plus z times k hat. And what I'm interested in asking now is, in 3 dimensions, let's say I define a surface that is a cube. And I'm interested in asking the question, how much stuff is coming out of this cube, right? So if you think about that, you've actually, if I wanted to write that integral in dimensionless form, this cube is a closed surface, so it's a closed surface S. I'm going to integrate over that closed surface the number of particles per unit volume, right? So this is number per meter cubed, times the velocity, which is a function of where I'm located, dotted with n hat dA, right? So conceptually all I'm doing is I'm taking this cube and I'm breaking it up into a bunch of little dAs, and I'm asking the question, how much stuff is passing through each of these dAs, okay? Now if I go further, I can actually think about that as being this surface integral consists of basically 6 surfaces, right? I have this side of the cube, this side of the cube, this side of the cube, and then the sides of the cube that lie on the xy plane, on the xz plane, and on the yz plane. And so I'm going to have integral over the sort of face 1 of this stuff, plus the integral over face 2 of the stuff, etc., all the way integral over to the integral over the 6th face of the stuff. Let's take a second to think about a couple of those surfaces. So first let's think about this surface that's in the xz plane, right? So I'm talking about this surface here. So first of all, let's think about what n hat is for that surface. Let's call that surface number 1. So for surface number 1, we have an integral, and we're integrating with regard to x and z, right? So x goes from, let's say, 0 to 1, and z goes from 0 to 1 on that surface. N hat is going to be a unit vector that's pointing out, right? So n hat will be in the minus j hat direction, right? In the minus y direction. dA will be dx dz, right? And then finally, my velocity is going to be x times I hat plus y times j hat plus z times k hat. But for that particular surface, y is 0, right? And so for that particular surface, I have 0 j hat, dot j hat. This whole thing is 0, right? So that first face is 0. And the reason is that this velocity field in that face is all parallel to the face. There is no velocity in the y direction at y equals 0, right? And the same thing actually applies to the face that's over here in the yz plane, and to this face here that's in the xy plane, right? All 3 of those faces are going to be 0 as the flux. So I'm down to 3 fluxes that I have to deal with. I need to deal with the flux on this face, which will be the integral, double integral from, let's see, I'm going to run from y equals 0 to 1 and from z equals 0 to 1. So I've got x, which is going to be 1 times I hat, plus y times j hat plus z times k hat, right? All dotted with, well, the unit vector for that surface is, the normal vector for that surface is I hat, right? And it's plus I hat, it's going in the positive I hat direction. And finally, I've got dy, dz are going to be that's going to make up my differential area element on that face. So now I've got 1 times one I hat dot I hat, so this is the only thing that's going to come out of this dot product is a 1. So I have the integral from 0 to 1, 0 to 1 of 1 dy dz, which, not surprisingly, gives me the area of that face, which is 1. So the total flux will be 1 particle per second out of this face, plus 1 particle per second out of this face, plus 1 particle per second out of this face. So for this particular case, I would end up getting 3, assuming that my density was 1 particle per meter cubed, or 3 rho for an arbitrary number of particles per meter cubed. So these are 2 really simple examples, the sort of polar case and the cube case, but I hope it's helpful for at least understanding the way that you think about the stuff that make up a flux integral. Right? In general, if you're integrating around a closed surface, whether that's it could be a closed contour, or it could be a closed surface, right? So, sorry, this should be dl. So for 2 dimensions, your flux is this integral around a closed contour of whatever the vector field is, dotted with a normal vector times dl, right? So you have some length dl, and this is the normal vector for that little bit of length dl. And similarly for flux for a closed surface, you need to ask the question, what's the unit vector for that little bit of area dA? So you take whatever the vector field is you're calculating, dot n hat times dA. So finally, I just want to comment a bit about some notational things. We often talk about flux density, which has units of either flux per meter cubed if you're talking about area, or flux per meter if you're talking about flux through a curve. Notice that that's a vector, right? It's got to be directed because you're integrating that over a surface, and you need to know information about what the orientation of that surface is at each point. Okay? So a couple of things that we've introduced in this. One is this sort of idea of flux density. One is this idea of looking at what that unit vector is and taking a dot product in order to figure out that. And finally, this idea of talking about flux through a closed surface as being the amount of stuff that's coming out of that closed surface.